Hello physics students, this is Dr. Brenzy here, and we are in a homework video for lesson 2.1.3. I'm going to just go through the odd problems 1, 3, and 5, just to give you an idea, a flavor for how these problems are done. I am going to change some numbers here so that you can actually practice with the real problems. So let's say here that this is a 10 kilogram bucket of water accelerated upward, and let's say the braking strength is 100 newtons. Okay, so it says draw the free body diagram of the bucket, or for the bucket. Okay, so let's do that. And I'm going to go ahead and erase all this. All right. So the bucket is being accelerated upward for some reason that's not reading well. Bucket. And it's being accelerated upward by a cord. So we're going to call this a tension force, F sub T. And we also have what other force acting on the bucket? Well, hopefully you told me that there's gravity also acting on the bucket. So F sub G, which equals negative M times G. And if I remember right, I told you that for my sample problem, the mass is going to be 10 kilograms. All right, so this force due to gravity would be negative 98 newtons. All right. And we have these two forces acting on the bucket. We have the cord pulling up on the bucket, and we have the force of gravity going down. So that would be part A for this problem. Part A. All right. Now for part B, if I remember right, we want to find the acceleration, the maximum acceleration we can lift this up before we end up breaking this cord. And the cord breaks when the tension force is equal to 100 newtons. So I have to make sure that the tension force remains less than 100 newtons. All right. So how do I figure out what the maximum acceleration is going to be? Well, I have to use Newton's second law. Newton's second law states that the net force F net equals, but put that in a different place. Let's put that right here underneath the tension. F net equals ma, mass times acceleration. What is F net? That's the sum of all the forces, right? So we have our tension force minus 98 newtons equals mass, which is 10 kilograms times acceleration A. All right, so I have two variables, two unknowns, but I do know that this cannot be any greater than 100 newtons. So that means that this, let's see, 10 times A has to be less than 100 minus 98. Okay? All right, so 100 minus 98 is 2. So if I divide both sides by 10, it turns out that I get an acceleration that is less than 0.2 meters per second squared. All right, so for this example problem, that cord would break rather quickly, right? You're going to get a different answer for your actual problem, but for this sample problem, I selected some masses and some braking strengths that were somewhat silly, because 0.2 meters per second is not a very large acceleration. All right, so that's problem number 1. So problem number 3, let's go back to our homework thing here. It says, if a net horizontal force of 132 newtons is applied to a person with a mass of 60 kilograms, resting at the edge of a swimming pool, what horizontal acceleration is produced? Assume that friction is negligible. Well, let's say that this is, instead of 132, let's say that this is 400 newtons. And let's say that this person has a mass of 40 kilograms. All right, so, well, again, it seems like, what do we want to find? We want to find the horizontal acceleration that this person would experience if they had that force applied to them and their mass was 40 kilograms. Well, again, this is a pretty straightforward application of Newton's second law, because we are given the net horizontal force. That is the net force. So if F net equals ma, then I can just divide both sides by m, and my acceleration has to equal F net divided by m. All right, so if I took the net net force, 400 newtons divided by 40 kilograms, I would get 400 divided by 40, and that acceleration would be 10 meters per second squared. So that's a really straightforward problem. All right. Now let me show you number 5. And I know that this one isn't all that straightforward. So it says here, a crate with a mass of 32.5 kilograms initially at rest on the warehouse floor is acted upon by a net horizontal force of 140 newtons. What acceleration is produced? Well, that sounds exactly like problem number 3, right? So you can figure out problem 5a. How far does a crate travel in 10 seconds? Okay. Well, and then what is the speed at the end of the 10 seconds? Well, I'm just going to give you some clues on this one. So let's say that I find that the acceleration, let's say I discovered that the acceleration, this is part B, 5b. Let's say that the acceleration equals 10 meters per second squared, just like I found it in problem number 3. All right, this is just like a for instance. Okay, and then it said I traveled it says how much time does it take to cover a certain distance? Let me double check that. What acceleration? How far does the crate travel in 10 seconds? All right, well this was, all right. So to figure out how far the crate travels in 10 seconds, well, we know that displacement equals initial displacement. And we can assume the initial displacement is 0. Plus initial velocity times time. Plus 1/2 a/t squared. You're going to plug in the 10 right here. You know the time's given to you in the problem. So you know that. And you got to read the problem carefully to figure out what the initial velocity is. So all you need to do is plug in values for that, for this. You know what this is because you figured that out in problem A. And you're going to know the time again because that's also given to you. And that will give you the distance that our box covers in that much time. Likewise for problem C. If we want to find the velocity, instead of using this displacement equation, what equation do you think we'll need to use? And then, once you figure out what equation you need to use, what variables are you given, or how could you figure them out? Okay, and then you will use that to find the velocity that the box will end up at the end of that amount of time. Okay, so I've covered problems 1, 3, and 5. I've just given you hints for problem 5. That way you can do more of the thinking as you go along. And hopefully this has been helpful. And I look forward to seeing you soon. All right, bye.